Hello and welcome back. Let's do some more examples involving trigonometric identities. So we previously saw that we had negative cotangent times sine is equal to negative cosine after some signs cancelled. We used one of our Pythagorean identities here to rewrite secant squared minus 1 as sine squared over cosine squared. So let's look at this next one. We've got secant x divided by cosecant x. Have secant x divided by cosecant. Cosecant. And again, my strategy is almost always to rewrite things in terms of sines and cosines, so I can simplify things as much as I can. So the secant is 1 over the cosine, and the cosecant is 1 over the sine. So I can rewrite everything in here with sines and cosines because of my reciprocal identities. So the secant of x is just going to be 1 divided by the cosine of x, and the cosecant is going to be 1 divided by sine of x. But if I'm dividing a fraction by a fraction, I simply multiply by the reciprocal. So I have 1 over cosine times sine over 1. I'm dividing by a fraction. And this simplifies down quite nicely. This is just going to be sine of x divided by the cosine of x, which, if we come back to our original options, there is one of these that is sine divided by cosine, which is the tangent. Tangent is sine divided by cosine. And this would be our simplification of this guy here. So we'll have the tangent. It's going to be this guy. Cool. So when we look at the next couple, we've got 1 minus sine squared and just sine squared by itself. So if we look at these guys, our options up here, 1 over the cosecant squared looks pretty simple. So maybe the simple ones match up. So if I look at 1 over the cosecant squared, well, which one of these is going to match up with that one? The cosecant squared, I can simplify the cosecant squared into a sine pretty easily. So it really feels like those guys are going to match up. Let's start, and here we'll maybe work in reverse a little bit. If I start with 1 over the cosecant squared, I know that the cosecant is just 1 over the sine. So this is going to be 1 over the sine squared. And again, when I simplify this, dividing by a fraction, I multiply by the reciprocal and everything here. This is just going to be sine squared. So this is actually one of the simplest ones. And then what's left over is to rewrite 1 plus sine squared as the cosecant squared minus cotangent squared plus sine squared. So let's actually work through that one and see why that one works. So I'm going to start again with a more complicated end, and we have cosecant squared minus cotangent squared plus sine squared. And what we want to do is we want to write this as 1 plus sine squared. So the question is, are these guys equal to one another? And we can already see that they kind of match a little bit with the sine squared. But do the first ones match? Is cosine squared minus cotangent squared equal to 1? And that's where we go, Well, yes. This we have lots of squared functions in here. They look like our Pythagorean identities. So let's remind ourselves what our Pythagorean identities are. Sine squared plus cosine squared is equal to 1. 1 plus secant. Wait a second. 1 plus tangent squared is equal to secant squared. And we had cotangent squared plus 1 is equal to cosecant squared. And this last one is going to be the most helpful because we've got a cosecant and a cotangent. So we want cosecant squared minus cotangent squared. Well, if I just subtract cotangent squared from both sides, what am I left with? Well, 1. And I've got the cosecant squared. And if I subtract the cotangent squared, oh hey, these guys are just equal to one another because the sine squareds match and the cosecant squared minus cotangent squared, that's just equal to 1. Everything is just equal here, which makes that pretty nice. And then we can check our answer, and we got it correct. So let's maybe do a couple more. So we've got secant of theta is equal to x plus 1 over x. And we want to find an expression in x for tangent theta. So let me maybe zoom in just a little bit. So I want to write tangent in terms of x. So let's come back here. So in our example, we said that our secant of our angle theta was x plus 1 over x. And the question is, what does tangent equal? So if only there were a way to relate secants and tangents together. If only there were a way to relate secants and tangents together. We have a way to turn secants into tangents. We know that 1 plus tangent squared is going to be equal to secant squared. So how do I solve for the tangent in here? Well, let's write this down. So I have 1 plus tangent squared is equal to secant squared. And then I want tangent by itself. So I'm going to subtract 1 from both sides. And then, in order to find the tangent, I'm going to need to take the square root of both sides. But when I solve this equation, I could take the positive root, or I could take the negative root. I could take the negative of this answer, square it, to get the same thing as I would the positive root. So here's what I need. I need plus or minus the square root of secant squared minus 1. So let's start simplifying this. So the square root, I'll add the plus or minus at the end. Secant squared, not x. What am I doing? The angles have to match in order for this identity to work. So secant squared theta minus 1. Well, I know what secant is, so I can just square that. So this is going to be x plus 1 over x squared minus 1. Let's start squaring this so that we know exactly what's happening. So when I take a fraction and I square it, I just square the top. So it's going to be x plus 1 squared over x squared minus 1. this fraction here, I want to put everything over a common denominator so I can combine these. So 1 is just going to be x squared divided by x squared. So if I turn 1 into x squared divided by x squared, I get all this. And then I can start consolidating my fractions. Let me write this a little bit bigger for the next line. What is x plus 1 squared? It's going to be x squared plus 2x plus 1 after I FOIL everything, minus x squared, all divided by x squared. And some things start to cancel. X squared minus x squared. So I get 2x plus 1 over x squared, and I'm taking the square root of everything. And then here, I can just take the square root of the top, divided by the square root of the bottom. Well, the square root of x squared is just x. And this whole thing, tangent of theta, is going to be plus or minus 2x plus 1 divided by x. And when I come back, I see my answer exactly. Plus or minus the square root of x plus 1, sorry, 2x plus 1 over x. And then I can check the answer. Cool. Let's do one more. Maybe we'll find some other ones. So we want to write the expression in terms of sine and cosine, then simplify the expression so that no quotients appear and all functions are of x only. So it's a lot of instructions, but this should be fairly straightforward. Our example has tangent times cosine. So let's just write that down. Tangent x times cosine x. The first step is to write the expression in terms of sine and cosine. So let's just do that. Tangent is sine divided by cosine. And cosine is just already cosine, so nothing more to need there. And then we need to simplify the expression so that we don't have any fractions, no quotients, and all functions are of x. Well, sine x over cosine x times cosine x, cosines cancel, and we just get sine x. And oh hey look, no fractions, everything is simplified, and this should just be sine x. Perhaps they don't want the parentheses around there. Okay, so now we know not to put parentheses around there. And a few more are going to be like this, where you're just writing things in terms of sines and cosines. And quite often these are going to be multiple choice, so that you have a little bit of an idea of what your answer should look like. So have a go at these. I think trig identities can be a lot of fun to try to use and to try to match exactly what's on there. And which trig identities do we have thus far? We have the reciprocal identities. We have the Pythagorean identities, where you have some squared functions. We have the quotient identities, where tangent is sine over cosine, and cotangent is cosine over sine. And we have our odd and even identities. So essentially you can pull a negative sign out of a sine function, but a cosine of a negative angle is just the cosine of the positive angle. So negatives don't matter for the cosines. And that's where I'll stop.